Hello everyone. Today in this video, we are solving a problem on the concept of simple pendulum. The problem is like this. What will be the time period of a simple pendulum when it is in a lift and lift is having different possible kinds of motions, right? So we'll start with the first case, right? When the lift is coming down with an acceleration here. You know, when body is in a lift coming down with an acceleration A, effective acceleration effective acceleration, a resultant you can call as G minus A. Effective acceleration, a resultant is equal to G minus A. That's because the normal reaction acts in a upward direction, right? We have discussed this in the laws of motion. I'm just giving you the concept here, right? So what happens to the time period in that case? Time period T equal to 2 pi into root of, in the place of L by G, at effective acceleration, that is 2 pi into root of L by G minus A. That's the first case. Next, when lift is moving up with an acceleration V, body becomes heavy when you are moving up in a lift because A resultant becomes G plus A. You can feel it in a normal day-to-day life also. You feel light when the lift is coming down and you feel heavy when the lift is going up. So in that case, the new time period will become 2 pi into root of L by G plus A. Notice that here denominator is less, so the time period increases. The denominator is more, so time period decreases. That's the second case. Look at the third case. In the third case, there is a lift. The ceiling of that, a simple pendulum is attached. Now, this lift is now moving in a horizontal direction with an acceleration V. So this frame becomes a non-inertial frame. To make the non-inertial frame an inertial frame and apply the Newton laws of motion, we shall imagine a pseudo force of the bow of the same magnitude but in the opposite direction. So it is experiencing a horizontal pseudo force in the opposite direction. Of course, its weight is acting in the downward direction. The resultant will be somewhere here. That's the A result. A resultant is the vector sum of these two, where these two are perpendicular to each other. So A resultant is root of acceleration of that lift square plus acceleration of the gravity square. Because when the two vectors are perpendicular, A resultant is equal to, resultant of the vectors is root of p square plus q square plus 2pq cos theta. That theta is 90. So cos 90 is 0. So the new time period will become 2 pi into root of L by root of a square plus g square. This is also more than g. Denominator increases, so the time period decreases. That's the third case you are talking about. Now, let's talk about the fourth case, when the lift is falling freely. So when the lift is falling freely means it is falling with an acceleration equal to acceleration due to gravity. It is coming down, an acceleration equal to acceleration due to gravity itself. When the lift is coming down, we have already written a formula. 2 pi into root of L by G minus acceleration A. Now it is falling down with an acceleration G itself. So 2 pi into root of L by 0. Something by 0 is infinity. So it will have an infinite time period. So This pendulum has infinite time period, means it will never be able to complete its oscillation, right? That's the case D. And finally, we have one more case, E case. When moving with a uniform velocity, when the velocity is uniform, it has no acceleration. So the G value remains the same. Time period also remains same as a normal simple pendulum 2 pi into root of L by G, whether it is in a lift or not in a lift. So when you are moving with a uniform velocity, it doesn't make a difference whether you are moving up or down. In both the cases, time period remains same. This is how the time period of a pendulum is affected in different possible cases. Thank you for watching.